the problem 1. Medium 1 has electrical permittivity epsilon 1 equals to 1.5 epsilon naught farad per meter and occupies the region to the left side of x is equals to 0 plane. And medium 2 has the electrical permittivity epsilon 2 is equals to 2.5 epsilon naught farad per meter and occupies the region to the right of x is equals to 0 plane. If E1 is in medium 1, that is E1 is equals to 2ax minus 3ay plus az volt per meter, then E2 in medium 2 is. Here just observe what is the data given to us, that there is a boundary. That boundary is clearly x is equals to 0 boundary. So at x is equals to 0 boundary, we are supposed to apply the boundary condition. So before that, for less than 0 we have some electric field that is given to us. For greater than 0 we are supposed to obtain the electric field. So before that, what is x is equals to 0 boundary? X is equals to 0 indicates a plane which is yz plane. So let us take this is the yz plane, that what we have. That x is equals to 0 corresponds to as a yz plane, and less than is negative x-axis, greater than is called as positive x-axis. So just you have to remember, recollect the rectangular coordinate system. In the rectangular coordinate system, so we are supposed to take all these planes, right? Now what I do is I will directly draw that yz plane. So let us take this is the yz plane, that is at this plane x is equals to 0, right? So below this x is equals to 0, always it is negative x-axis, that represent this one as a negative x-axis, and above this one it is a positive x-axis, right? Now the different parameters are given to us. Yes, at less than this 0, x value as 0, epsilon 1, that what we have, and in this region it is epsilon 2, right? Here E1 is given to us. Here we are supposed to identify what is E2, right? Now clearly we are supposed to decompose this electric field intensity as the tangential component and normal component, because we have the relation between the tangential and normal only. We have no relation between x, y, z, right? So what is the tangential component for the given condition or given scenario? What is the normal component for given scenario? Like just remember or the recollect our planes, that is yz plane, that what we have. For yz plane, what is the vector which is normal to it? Always x, right? So for this x is equals to 0 plane, that is nothing but yz plane. If you have any component which is in the direction of x, which is said to be the normal component, the remaining all are tangential components. So what is the equation of E1 here? Equation of E1 is 2ax minus 3ay plus az. So in that one, what is the normal component? The component which is in the direction of x, that may be in positive x direction or negative x direction, whatever may be the direction. If the component is in x direction, clearly it is said to be the normal component. So for this E1, directly I am writing the normal component with, that is nothing but your 2ax. That the identification is very important here, that the tangential component we are observing for the boundary, right? And that's not tangential, normal component. So E1n is equals to 2ax, that is the normal component. The remaining all are tangential components. So E1 tangential component is directly write down this one as minus 3ay plus az. Did you get it? So clearly the tangential component is normal to the boundary, normal component is normal to the boundary, and the remaining all are tangential components. Now try to get your boundary conditions for electric field. The tangential component is always continuous, that there will be no change in the tangential component. So wherever you have the tangential component, directly write down in the second medium, no need to change it. So here what I do is I will take this E2 tangential component same as our E1 tangential component, which is equals to minus 3ay plus az. No need to change it. But what about the normal component? The normal component is discontinuous. It is not equals to the previous one. So for that, the normal component of the flux density we are supposed to take. The normal component of the flux density is continuous. That what we can write is d1n is equals to d2n. d1n is equals to d2n corresponds to E1n multiplied with epsilon 1 is equals to E2n multiplied with epsilon 2. From that, what we require is E2n, right? So E2n is equals to, directly write down here. So E2n is equals to epsilon 1 divided by epsilon 2 multiplied with E1 n. So epsilon 1 by epsilon 2 is nothing but epsilon r1 by epsilon r2, or they are given directly, we can substitute there. So clearly from this E2n can be obtained with this simple relation. What is our epsilon 1? Epsilon 1 is given as 1.5 epsilon naught divided by, so epsilon 2, what is epsilon 2? 2.5 epsilon naught. So it is 2.5 epsilon naught multiplied with E1n. So what is E1n? 2ax. Simply it is 2ax. So it is 15 by 25 multiplied with 2, so approximately equals to 1.2. So which is equals to just 1.2 ax. So very simple one. That what we got is the decomposition. So the electric field was decomposed as normal component and tangential component. The tangential component as it is, it was transferred to the second medium or through the boundary, but the normal component was changed. Initially it is 2ax, but now the magnitude was changed to 1.2 ax. Now the combination of these two is nothing but your E2. So just add them. If we add, then what we get is 1.2 ax minus 3ay plus az volt per meter. Simply this is the answer what we require. The electric field component in the second medium is the combination of E2n and E2t. That is simple answer. Two dielectric media with permittivities 3 and root 3 are separated by a charge free boundary as shown in figure below. The electric field intensity in medium 1 is E1 and makes an angle of alpha 1 is equals to 60 degrees with the normal. Then the angle made by E2 with respect to the normal, that is alpha 2 is. Here clearly observe what is the data given to us. The electric field is traveling from one medium to another medium, that is exactly at the boundary it is taking refraction, that what we discussed earlier. Now these two angles are given to us, that is, let us take this is alpha 1 and this is alpha 2. In our analysis we took this one as theta 1 and this is theta 2. No problem, whatever may be the notation. So here the two angles alpha 1 and alpha 2 are given to us, whatever may be the notation, take them as it is, no problem. Okay, so this is angle of incidence and this is angle of refraction. So here a very simple equation, that is law of refraction for our electric fields, is very much useful. At the boundary, what is the law of refraction? We know tan theta 1 divided by tan theta 2 is equals to epsilon 1 divided by epsilon 2. So blindly remember theta 1 epsilon 1, theta 2 epsilon 2, right? So here just we need to replace, or we need to substitute all these values from our figure. What is theta 1? Angle of incidence. What is angle of incidence? Alpha 1, which is equals to 60 degrees. Substitute here tan 60 degrees divided by, what is theta 2? Theta 2 is angle of refraction angle, that is alpha 2. So clearly it is tan alpha 2. We don't know how much it is, we are supposed to calculate it, which is equals to, what is epsilon 1? Epsilon 1 is equals to 3 divided by epsilon 2. Epsilon 2 is root 3. So tan 60 by tan alpha 2 is equals to 3 by root 3, which is nothing but simply root 3. Tan 60 is root 3, root 3 will be cancelled, which corresponds to tan alpha 2 is equals to 1. That implies alpha 2 is equals to 45 degrees. So this is the answer. It's a very simple one. So if you know the refraction, law of refraction for our electric fields, then it is very easy to solve the problem. Like this, different problems will be given for our boundary conditions, purely depend upon the boundary conditions which are satisfied, which will be satisfied for electric field and magnetic field. That we are supposed to remember what is the relation between tangential and normal components. So with this one we can conclude our boundary conditions.